So this is what I'm explaining you yesterday, that the balanced word and Stamian words. And so the most important theorem around Stamian word is the Morse-Hedron theorem, which is a classical theorem characterizes this infinite sequence in 4 ways. The Stamian word is understood as a aperiodic balanced word. This is one way of understanding. And the other way is a mechanical word of irrational slope. And the fourth way, the third and fourth is almost the same. So x is a coding of irrational rotations by putting one point with the partition point 1 minus alpha. That's what I explained to you yesterday. And so this is the definitions of a mechanical word. Just a review. So alpha is called slope, and the rho is called an intercept, and the word produced in this formula is a Stamian word. Okay, so you can look at this picture to understand well that starting from rho, and then the slope means alpha, and alpha is less than 1. So rho and the increase happens if in this picture, and alpha plus rho, between alpha plus rho and 2 alpha plus rho, then we have a jump in this way. So if you have a jump, then we add 1. The other case, this is 0. Okay. And another way to understand the balanced word or Stamian word is the coding of rotations. So it's just a coding. And so in this picture, rho in the anti-clockwise order is rotating. And so rho is a starting point and alpha is a rotations. And so I draw this bold line 0 to 1 minus alpha is the region that we put 1 for symbols, and otherwise we put 0. Okay, so this is the coding of rotations. So let me review this one. So it's a 2-interval exchange. So RA goes to TA and B goes to TB in this manner. So it's just exchange 2 intervals and in this case the alpha is the slope of rotations, and 1 minus alpha is written and above. This is a very important point, so just remember this place. Okay, now we consider this 1 minus alpha, and this 1 minus alpha is understood as a rotations, inverse rotations of 0. So the point T inverse of 0 means that this is minus alpha rotations, but we start from 1, so this is 1 minus alpha. Okay, and then so we put T inverse of 0. This is in the symbol space, this is a set of discontinuities. And then so we go ahead by T minus 2, T to the minus 2, 0, and T to the minus 3, 0, then T to the minus 4 in this way. So this picture is important to understand my lecture today. So first line, so as I said, that the 0 to T inverse of 0 is called cylinder, which gives us the symbol 0. And between T inverse 0 to 1, then this is a region called 1. So if you fall into here, this is 1. Okay? This is just a review. But the second line, so if you look at this picture, let's start with some point on 0, 1 interval. Okay, so in the middle. Then, so it's rotation is alpha. So if you rotate this point, then starting from 0, 1 interval, so 0, 1 point is the starting the initial letter is 0, but the next one is 1, because by rotation rotation is alpha. Clear? So which means that whenever you start with the range between t minus square minus 2 to t minus 1, then you receive a letter consecutively 0 and 1. Okay, this is the coding. And if you start with 1, then the next second you go to 0 interval, because in this picture that the 0 is larger, the interval 0 is larger. Okay, and otherwise, so if you're maybe I cannot write, but can you see my cursor here?
Yes.
Hope so.
Yeah,
so
yes.
If you start from here, so if you start from 0, 0, I hope you are seeing my cursor. I'm not sure.
Yeah.
Yes, yes.
Yeah, okay. So if you are starting from this point, the next stage is surely 0. So if you start 1 second, then the rotation, this amount is the rotation. So if you start from here, the next 1 second, you are somewhere here, but never going to 1. Okay? So you start from here, then you surely receive 0, 0. And if you start from here, then you surely receive 0, 1. And so if you start from this third interval, then you surely receive in 2 seconds. First letter is 1. The next you go here. So this is 1, 0. Hope you understand what I mean. So these 2 letters means that in 2 seconds you get 2 letters. 2 letters. Okay? This is the rotations. So we start with, this is the 0 interval, and this is the 0, 1 interval. And so if you are in interval A, then you receive 0. And if you are in interval B, you receive 1. Okay? So initial letter must be 0. And the initial letter must be 1 here. But if you are here, then the next second you are going to this region. So in the 2 seconds you get 0 and 1. So this is the point that I'm talking remote, so I don't see your face. So if you understood, then is it okay? Or if you are not understand, then I repeat.
No,
This
please
is the most
repeat
important
one.
part.
Yeah, please repeat one.
Okay.
Please repeat.
Okay. So then so this first step is understood. Then this third, fourth is very easy. So we consider the inverse image of t to the minus 3. Then we get this. So you in the future 0, 0, 0 here and 0, 0, 1 here, because in these regions the next digit is 0 and the next digit is 1. So what you get is 0, 0, 1. And here, then we start with 0 and you go to 1 region and then 0. So what you get is 0, 1, 0. And here, this is 1 and 0, 0. Okay? So in this way, and once this t minus, so if you repeat these rotations to t to the minus 4, then we get this kind of decompositions. So what you get is the letters. So we have 5 words, 5 words. Okay? This is the coding of irrational rotations. Just remember, so what I said, so the Stamian word, you remember, yesterday I said that the cardinality of the word of length n is equal to n plus 1, n plus 1. And this is the definition of Stamion world. And now you understand. So by looking at this picture, so whenever you start in this interval, you are starting from here, then you get this 0, 1, 0, 0. And if you start from here, then you get 1, 0, 0, 0. And you start from here, then 1, 0, 0, 1. So this means, this picture means, so number of words in this coding is 5. Surely 5. Because so the sections obtained by this T inverse of 0 is 4. So we have 4 cutting points. So we have 5 intervals. Okay. So in this way, so we remember. So this Stamion word is that the cardinality of this number of letters is n plus 1 exactly fit into this framework. Okay. So this is this figure is extremely important in my lecture. So this means, and as I said, that this Morse-Hedron theorem, that so this Stamion was exactly the same as coding of irrational rotations. Okay, and this means that the Stamion words of this slope means this, so the alpha is this length, the slope alpha, then you obtain, so Stamion words of length 4 is 5, and this is listed here. Hope you understand. So, and so this also proves that this irrational rotations, by using this irrational rotation, you get Stamion word. So this is another proof of a Stamion word. So this is surely a Stamion word. I hope you understand. Okay, so this is the supplement of yesterday that I missed talking about this. This is important. So please, so if you have any questions, please interrupt. This is important. Otherwise, you get nothing. Is it okay?
Yeah.
Okay, then let me continue. This is an extremely important picture. Okay, so let me come back to the Lagrange spectrum. And the definition is like that. So for any x, given real number, irrational number, and so we find this equation, inequality has infinitely many solutions for some c, and take the supremum and collect all the supremum, then it is called this Lagrange spectrum. And another way of looking at is written in this way, that it's a cozy form. So limit sup of 1 over n and nx, and this is so distance to the integers. And this number 4 into so this square root of 5 and infinity. And yesterday, this is very well linked to the Stamion sequence. Let me repeat. First of all, this set is closed, and this proof I cannot say, but there are some proof to show that this is closed. And this is a rather important theorem by Kuzik. And second result is that this set, and yesterday I said, has accumulation point, minimum accumulation point 3. And so below 3, so between 0 and 3, then the spectrum is discrete. And this discrete part is completely described by balanced words. So this this kind of word gives complete descriptions of this spectrum below 3. And the third one is that this yesterday I said 6, but the exact number is called the Feynman's constant. So this is something like 4.5 something, And so from here on, then all of the number belongs to the Lagrange spectrum. Okay. So I tried to explain you a little bit more about the relation of this Stamian sequence and the number theory. So in fact, I met this Stamian sequence by the following problem, which is a multiplicative analogy of Markov Lagrange spectrum. And I cannot today I cannot explain you in total this setting, but so I just give you one example. So start with alpha, this is an irrational number, and so we start with b greater than equal to 3, and consider this quadratic unit. So minus b plus square root of b squared minus 4 over 2. And then, so we consider limit inf of, this c times alpha to the n, and take the limit inf of all of them and correct all the limit inf. In this case, this, you remember this symbol is the, distance to the nearest integers. So this must be between 0 and 1/2. Okay. And we get almost similar property. So first of all, this L of alpha is closed. And the minimum accumulation point is 1 over 1 plus alpha. And this is less than 1/2. So this is, because alpha is greater than 3. So this is something like 1/4, something like that. And then, this is discrete. This part is discrete. And this part is described by balanced words. Okay. And this part, if you come to this accumulation point, then we get all the Stamian words. And there exists some positive c less than 1/2, that the interval is contained in this L of alpha. So this is very, very similar. And the proof of this fact, we use a different, so yesterday I talked about this Perron formula, but we use a different formula to embed this problem. And so the proof is totally different. So maybe that first part of the proof is very, very different, but finally, we reach the similar phenomena. So we are very surprised that the situation is very, very similar. Okay, so next example that I want to show you is this is very close to the topic of this meeting, that Dong-Han Kim and Yan Bourgeois introduced a different complexity function than P of n, the factor complexity that I used to define the Stamian sequence. So this is called the R, return time complexity sometimes. So we consider the minimum length, the prefix of x, such that it contains 2 occurrence of subwords of length n. Then they showed that the infinite word is Stamian if and only if this new complexity functions is less than or equal to 2n plus 1, and the equality happens infinitely many times. And so by using this, they define some repetitivity constant, which is called the rep x, which is a limit inf of this quotient. So this r of rx of n over n. And so if you know this number, then one can discuss this number. And this number, and sometimes this is transcendental, and one can show by using this number. And they showed, so this part is not related to Stamian number, but if the Stamian, in a Stamian case, this number is very well computed. So they discuss a lot of problem around this. So return time complexity, and so this is of course related. Maybe you know the famous Roth theorem. So if you because if you have a repetitions like so two prefixes very similar, so we have similar words, then so if you cut off at some point of this number by a nice way, then we have a very nice rational approximations, and then this good rational approximation gives you some result on the irrationality measures of this number, and sometimes one can show this transcendence. So this and the Stamian world appears very, very nicely in this framework. And yesterday, Jean-Paul told us the Penrose styling. So I was inspired by, and I want to come back to the Penrose styling. Maybe you know the Penrose styling. So Penrose tiling is Penrose tile is a set of tiles written in this way. Sometimes this is called kite and dart. So this is dart and this is kite, and we draw some matching rule here. This shape is come from this black line, and the marking is written here. Okay, so the tile itself is just a polygon, and I'm writing some circular marking. And matching rule means that we must marking must continue across the edge. Okay, and this matching rules, then this Penrose tiling is very famous and tiles the plane, but only in non-periodic way. Probably you heard of it. And this is due to Conway, that he found a very nice structure, which is something like a worm, and he said this is now called the Conway worm. So in the Penrose styling, we have a linear structure, and this worm is a linear, so very similar to linear structures. And so every Penrose styling, you have a arbitrarily long worm, but ends up infinite. Okay, and surprisingly, so this if you make a coding on this line, this is a Stamian sequence. So one can understand this pattern by Stamian sequence. Okay, probably some of you heard the new discovery by Smith, Myers, Kaplan, and Goodman and Strauss. They posted a very nice tile. So the shape is like this. This is called Smith hat, and the Smith hat is better than Penrose in a sense that in the Penrose case we need two tiles. So two tiles, and then can tile the plane, but only in non-periodic way. But they found that only one shape. So Smith hat has this property. So this is called aperiodic monotile. So only one shape, and then you can tile the plane in this way. Okay, this is a rather surprising discovery, and this one. So this white shape is just the reverse. So one can flip the tile. Okay, and so I just want to mention about my paper with Yoshiaki Araki, that we found a different proof of this aperiodicity, which means that it can tile the plane, but only in a periodic way. Okay, so this is this Smith hat and this style is slightly different. But in this paper by the four authors, so they said that this and this belongs to the same family and same property. It's just changing the ratio of the edges. So this belongs to the same family of aperiodic tile set. Okay, this is a Smith-Hart variant. Okay, and we found some substitution rule. This is a so schematic image of a substitution rule, and so maybe this is a bit not so easy to look at this, but if you look very closely around here, okay, around here or around here, then we have only two tiles. You see only two tiles are meeting. You see the direction is only two. And surprisingly, this one is a Stamian sequence. So Stamian sequence that, and it is written and produced in this way. And I wrote the substitution rule, and this satisfies the substitution rule very close to the Fibonacci, but slightly modified Fibonacci substitutions. And then, so what you get is this kind of pattern. Only we see so two orientations. So A, D, A, D, A, and D is just flipped tile. And this looks like a very, very linear structure exists. And this sequence is a Stamian sequence of slope of this number. So in this way, so spontaneously, so Stamian sequence appears in very interesting programs. Okay. So Stamian sequence appears rather spontaneously. So we don't know the exact reason why the Stamian sequence appears, but still I feel very interesting that so sometimes my vague intuition is that whenever you find some structure, then if you look at some ideal situations where, for example, the temperature getting lower, or sometimes we say entropy goes to zero, to make it make something like crystal structure. So in such a case, we often find such a beautiful structures in the limit. And so I don't know the exact reason, but my my intuition is that so this is prevalent, and I want to understand why that this Stamian sequence appear very often in so this number theory and other. This is so Penrose tiling may not fall into the number theory, but we find it very interesting, probably. And what you find is a surprising occurrence of Stamian sequence. I think the Conway worm is already surprising, but now Smith-Hart is really different tiling, but we find so Stamian sequence again. Okay, so this is the so I stop this introductions and come into my topic today. And today I just want to show you so idea of Yastomi, but so this part so is his paper, but I don't want I just want to make it much easier by using this picture. Okay, so maybe you can understand by this picture very easily that so we start with the unit square. Okay, and first we draw the line of slope 1 starting from origin. This is a slope 1. Okay, second we draw the line of slope 1/2. Then it meets at 1/2. Then we consider this is a torus, so we go here and then I continue. Okay, so this is the second step. So the third, we consider the slope of 1/3. This is a 1/3 slope, 1/3 slope. Okay, then so we come here, and then it goes here, and so this place is 2/3. Okay, and the 2/3, then you go this way. Hope you understand. And then I did it for until 4. So 1/4, then we go this way. The slope is 1/4 and meet at the right end and repeat in this way. So this meets at 1/2 again. This is 1/2. And then, so this one starting from 1/2, then this is 3/4, and then it comes back. So this is a partition. Okay. So now I hope that you understand the construction. Okay. So let me come back and compare this picture. Okay. This, in fact, so I want you to understand this part. Okay. So this picture and that picture is extremely related. Okay. So just remember this alpha. Okay. So this alpha may be around here. Okay. So we cut off in this way. So this place is in some sense 1 minus alpha. So the height is 1 minus alpha, like this. Then, so what we see. So what we see. So this point is minus alpha. Okay, because this slope is 1. So if you are taking this this is 1 minus alpha, then what you first meet, this point is minus alpha, and this is minus 2 alpha. Okay, this is minus 3 alpha. Hope you understand. So I'm writing, so this part, if I were at your place, then it's very easy to convince you. But so I tried to find this place in the picture. Okay, this is alpha, and this is so minus 2 alpha, and this is minus 3 alpha, and this is minus 4 alpha. Okay, where it is, I guess this is around here. No? So first you see 1. So this is minus alpha, and this is minus 2 alpha. Then maybe I made it. Okay, so this is minus 3 alpha, then minus 4 alpha is here. Because of these constructions, so you get so by cutting off at 1 minus alpha line, what you see is obviously this is minus alpha, this is minus 2 alpha, minus 3 alpha, and this is minus 4 alpha, modulo 1. Is it clear? Hope that this part so this part is the most important part in my talk today. So what is this picture? So this is can be understood as a totality of irrational rotations piled up in this picture. So this one, so if you cut off at this point, say, then this gives us one irrational rotation. But if you cut it here, you get different. So we get different system, different rotations. And if you are looking at this point, then we get the different slope. Okay, slope is here. This is smaller, and then gradually becomes larger, and then so around here, this is the picture what we saw, and then so we wrote in this way. So because of this number, maybe you see this is as I said, this is a balanced world you get by rotations. Hope you understand. So which means that so every cell you see gives us the same coding. So we are talking about the many irrational rotation at a time in this picture. So this is irrational rotations, and this is irrational rotation. This is kind of a modular space of irrational rotations, and so irrational rotation is piled up into this one picture. All the irrational rotation is here. All irrational rotations you can observe. And so now we look at this coding. Coding is given in this way. So as I said, that given this rotation alpha, then so this 5 words corresponds to the words of length 4, balance words of length 4 of slope this alpha. Okay, so what is this picture? So this picture tells us totality. So how many balanced words exist? So just look at this picture. We already know how many balanced words exist of length 4. Okay, I hope that this part is I just want to make us put a stress. This is a very important part. Is it okay? So this is a graphical understanding of balanced words. So by looking at only at this picture, one can count how many balanced words of length 4 exist. And this is the idea of Yastomi. And Yastomi was interested in this Markov Lagrange spectrum, original Lagrange spectrum, in the case where the limit case. The first accumulation point 3, and he was very interested in this number 3 and tried to understand all the numbers. And he drew this picture. And I think this picture is very interesting and intriguing. So this is a modular space of all the irrational rotations. I hope that I'm talking understandable talk. So this part is most important part. I want you to understand. Any questions? And so if I were at your place, then I will get many questions, but I'm afraid that so this is remote, so maybe you need to be brave to ask questions, or my talk is clear enough, so no questions. I don't know which. Hope that the latter is true, that what I'm talking is clear, so everybody understood. Hope. I'm not sure. Okay. So So this is a so I feel that the remote talk, I don't like the remote talk, in fact, that so I don't find your reactions. Hope that my talk is understandable. So now I'll give my result, small result. So so denote by B of NTU the cardinality of the set of balanced words. So balanced words is a Stamian words, or a finite Stamian words. And so we want, this figure gives us a very nice tool to compute, count how many balanced words exist. So our target is like this. So we fix the range of slopes between 1 minus t to 1 and law between 0 to u. Okay. So essentially this means that we are talking about around here. Because this is somewhat flipped. So closer to 1, then we are talking about this part. Okay. And then intercept is low, so alpha and low. So, and we want to count all the balanced words in this set. So what I'm saying is that we cut by rectangle this shape and count how many words you see. And this is B of N NTU. And we want to count how many. Okay. So counting how many cells in this given rectangle, maybe that as an if you are elementary school students or maybe junior high, I don't know. So there are standard way to count. The standard way to count is that so this is a picture, and I wrote until 8. So this is 1/8. So the slope is 1/8. Okay. And if you want to compute how many cells exist in this shaded area, then what you do is, so this dotted line is slope 1/8, and so this 1/8, and count how many new intersections exist. How many new intersections exist? So this red point is the point that which is caused by drawing the slope 1/8. So we count this red point. Okay. So this gives us an increase by adding this slope 1/8. So this increase is computed by this A. This is a definition, slightly complicated, but this is we compute. So this number of red points can be computed by elementary way. So one can compute in this way, and then add up until n. So we are talking about n, and m is moving until n, and sum up. Then this number is the number of balanced words. Okay. So this this is the number of balanced words, and number of balanced words is computed in history in many ways, but this one is a really geometric and nice way. Okay. And our target, so this the Yastomi gave the case where this intercept does not exist, and so this t and I introduced this t and u and computed this number, but this is just a continuation of his paper. Okay. And I want to talk about this small result. So the easiest case, so if you take t equal 1 and u equal 1, which means that we count all the balanced words, So this means 1, 1, and 1, 1. Then what you get is this sum. And phi j is the Euler functions, summatory functions of Euler functions. So this this can be computed, and there are many different proofs of this fact and found in several different papers. But anyway, this is one of the important formula, and so this formula is kind of a revision or more precise form of this by classifying by slope and intercepts. And so my small contribution is that so one can get some asymptotic formula. Then so we get this kind of bound, and nice thing is that this number of balanced words is cubic. So the main part is cubic. So growth is cubic, and then we have some error term. And the TU is given, then we have some error term. The technique is rather number theoretical, but if I have time, then I will explain a little bit. But the most important part that in my talk today is this one. So if you consider, this is the best way of explanations. So B of n minus 1. So you stop by so slope n minus 1 over n minus 1, and count all the balanced words. All the balanced words. Then, so maybe you know the Riemann hypothesis, which is a very famous open problem in number theory. And this Riemann hypothesis is equivalent to this formula. So the number of n minus 1 number of balanced words less than n, length less than n, is equal to n cubed over pi squared plus error term. And this error term is most important. So this error term is almost half of this 3. So 1.5 plus epsilon. And this is equivalent to the Riemann hypothesis. So I just want, this one is one of my central topic. So because I want to mention and put stress on this fact. Probably, so if you cut in this way, and so this, I did it until 4. So in this case, that this n is 5. So, and so this 5 times 5 cubed over pi squared. Okay. So question, how to count number of cells? And if you count number of cells efficiently, then you get the result, Riemann hypothesis. And by this, and we need some idea. So maybe this geometric idea, if you find, so if you give me some, if you have some idea how to compute this number, I'm very, very glad to have your idea. So because of this is directly related to the Riemann hypothesis. So so this formulation is very, very simple. So we just cut off by this balanced words, and then we only need to count number of cells appears in this picture. And I did by computer some experiments. It seems that this error is really small. So this is really accurate. So computer experiment really suggests that this, even that this is much smaller, but this can't be smaller. But anyway, so this error seems to be very, very small. But I don't know the reason why. So essential reason why. And of course, that so by using this formula, using this Euler summatory functions, and this is the Euler functions, there are many classical theory developed in number theory, and we have many so tools to compute and get an asymptotic formula. But if you boils down to this shape, then I believe that we have no hope. So if you manipulate this kind of computations, then so what you get is just an equivalent formula, equivalence. So the best thing is without brain, just attack this problem by this geometric way. And if you know some geometric idea, how to understand number of cells by these dissections, probably this is the best way. So number theoretical way probably does not help. I tried many ways, but the number theoretical way have no hope. Just this is my impressions. So anyway, so I to finish my talk by small maybe I have left 4 minutes or so. I try to describe the method, how to derive this kind of result. So basically, so what we do is a classical technique. So as I said, this has no hope, but this is a well-known method in number theory. So I try, maybe many of you are acquainted with this kind of method. So given some number theoretical functions, arithmetic functions, which is a map from n to the complex number C, and we introduce the Dirichlet convolutions and Möbius functions, maybe you know, and so the most prominent method we use is this generating functions, generating Dirichlet Ds. Then the Riemann zeta functions is defined, of course, by this Riemann, this Dirichlet Ds, and have Euler product in this formula, and then use Perron's formula. This is a classical tool to compute arithmetic functions, and sometimes we use the weighted variant, and in this case we use the least sum. So this is we need a different weight to get sometimes so by using this technique and study the very detailed study of the Riemann zeta functions, we obtain the prime number theorem. This is a classical development. And in this exact case, so t equal u equal 1, this is counting all the numbers, all the balanced words, then we have this formula and plug in. Then we get this least sum formula. And if the Riemann hypothesis is valid, then so what I do is something like that. So we have generating functions, and then shift this integral a little bit close to 1, and then cut off, truncate, and then move to the zero-free region. This is the usual technique to get this bound. And this is a very classical way to get the asymptotic formula. And so if you want to show something like this, so by cutting off by t or u, then we have additional difficulty. The number theoretical difficulty comes up. And so the point is that we need to compute this b of NTU, then we get some sum and treat so this ij, the coprime conditions, we use the Möbius functions and Möbius inversion. And this part is not so difficult, that ij is less than t is not so difficult, but this part, so u part, is a bit difficult. And we need to use some so-called large shaping inequality. which is written somewhere, to compute this sum and the large shielding inequality. Maybe I just show you what is large shielding inequality. So this one, and so I use this so large shielding inequality to compute in the general case. So anyway, so I just so want to encourage you to attack Riemann hypothesis in this way and give me any suggestions. Thank you very much for attention.
You will read carefully and then will be in touch. Why? Yeah, that I'll ask. Right? You will get the video also. Nikki, can you please send me this slide?
Yes, I'll send you. Yeah.
Thanks
Okay.
a lot. Thanks. Okay, thank you very much for lecturing, though remote. Maybe hopefully February you will be able to come. Yeah.
Hopefully that I really want to join you, but so because that I really want to feel what you feel. So I'm sorry I cannot make it.
No problem.
Hmm.
Thanks a lot.
Okay, thank you very much.
Thank you.